Now we know how to define integration, especially with respect to a measure. Now, when we have a sequence of functions, we can sequence of obviously measurable functions, we can define integrations for each integral for each function. Now, the question is, if we have some idea or some knowledge about the convergence of these functions, can we think of the convergence of the integrals of these functions? That means, for each function, say f n, we can define the integral with respect to a measure mu. So, the question is it possible to get some result, to get some idea whether there is any kind of convergence that is related to this sequence of integrals? That means, whether this entire integral which depends on f n, that means which depends on n, can be considered as kind of sequence of integrals, and whether that sequence of integrals or that set of integrals converge anywhere. Now, to this direction, we will discuss today only one theorem, which is known as Fatou's lemma, which is one of the most important theorem, or rather lemma, in the area of integration with respect to measure. So, today we will learn mostly Fatou's lemma, and I will discuss the rigorous proof of this lemma. Integration theory 2. Before going directly into the integration theory or the result or lemma that I intend to prove today, let us first do a small recapitulation of definition of a simple function. So, we have defined a simple function as an extended real valued function phi on this measure space x, script f and mu. Script f is a sigma field, is called a simple if it is f measurable and assumes only a finite number of values, say a 1, a 2, a n, that is small phi x equals to summation a I x a I. That means, if x belongs to a I, then I x takes the value 1, where a i's are disjoint intervals and union of a I actually is nothing but the whole space, that is x. So, this is the definition of simple function. We know this thing already. Now, the question, now we define the integral of a simple function as integral phi d mu as summation I equals to 1 to n a I mu of a I. Now, mu is the measure of a I is a set that belongs to the script f, as long as, this is very important, as long as plus infinity and minus infinity both do not appear in the sum. Now, unfortunately, if they really appear in the sum, then we say that the integral does not exist. So, when we define an integral, there is always one idea that integral may or may not exist. So, whenever we deal with some integral or theorems related to integrals, we usually assume or we impose some conditions under which we can ensure that the integral should always exist. And the definition of another definition of integration is that if f be a non-negative extended real valued function, real valued measurable function on the same measure space x script f mu, then we define integral of f as the supremum over phi integration phi d mu such that phi is simple and 0 less than equals to phi less than equals to f. That means, we have started with the definition of a simple function, then we define integral of that simple function, and then we use that definition of integration of simple function to define the integration of a more general function, but it should be non-negative. Only restriction is that it should be non-negative, extended real valued, but measurable. Measurability should always be there. So, after this, we can also define integration of a general any extended real valued measurable function. We have already seen in terms of this integral of a non-negative extended real valued measurable function. So, now we discuss some convergence theorems for integrations and expectations, and to this end the most important theorem, which is known as Fatou's lemma, that deals with this convergence of the sequence of integrals. This states that suppose we have a sequence of f n, we have f n which is a sequence of non-negative measurable functions which converges almost everywhere on a set E. Obviously, E must belong to script f, and this sequence of f n converges to a measurable function f. Then integral over E f d mu is less than equals to lim lower bar, that is lim inf of integral over E f n d mu. Now, we already know that this theorem, the condition, given condition of this lemma states that this f is nothing but the limit of f n. So, we can again write this instead of f, we can write this as lim inf of f n. That means, this Fathul's lemma can be or can alternately be written as integration limit as n goes to infinity lim inf f n d mu, which is less than or equals to lim inf integral of f n d mu. That means, we can take this lim inf inside and outside this integral sign, but there is always a inequality in this case. So, this is the famous Fathul's lemma. Now, we are going to prove this Fathul's lemma. The proof is little technical, but not really very complicated. I will explain the entire proof in detail. We already know the given condition is that limit of n tends to infinity, limit of f n x equals to f x almost everywhere, and f n x is non-negative. So, f n x is greater than equals to 0 or almost everywhere. So, this will imply that f x is greater than equals to 0 almost everywhere. Now, without loss of generality, we assume that since it is almost everywhere, we assume that f n x converges to f x for every x belongs to E, since mu of E complement equals to 0. That means, almost everywhere means that there is a set and the complementary of that set have a measure 0. Now, it is enough to show, given the definition of integral, the way we have defined integral in terms of simple functions, it is enough to show that if phi is any non-negative simple function with phi less than equals to f, then integration over E phi d mu is less than equals to lim of integral E f n d mu. So, then the proof follows immediately. Now, we have to consider two cases. The first case, suppose integration over E phi d mu equals to infinity, then there exists a measurable set A which is a subset of E such that mu a equals to infinity, and naturally in that case phi is greater than 0 on this capital A. Now, let us define a sequence of sets, that means set A n which is x belongs to E such that if k x greater than A for every k greater than equals to n. Now, since there is for all k greater than equals to n, so this is nothing but the intersection over k, that means intersection k greater than equals to n of x belongs to E if k x greater than A. Now, if you look at this sequence of sets very carefully, it is immediately clear that this sequence of sets A n actually increases in n or increasing in n, and union of A n over n contains capital A. Since phi is less than equals to lim inf f n, which is nothing but f, because f n converges to f almost surely. So, this sequence of sets play a very important role in proving this Fathul's lemma for the first case, that means when integral phi d mu equals to infinity. Now, by continuity theorem of measure, we can easily write limit n goes to infinity mu of a n equals to mu of limit n goes to infinity a n. Now, limit n goes to infinity a n is nothing but union of a n equals to 1 to infinity, as a n is an increasing sequence of sets. Now, what is A? A is x belongs to E phi greater than A greater than 0, and which is actually a subset of, if I write f greater than A, that means subset of x such that f greater than A, and this is again contained in, or this is a subset of limit n goes to infinity a n. So, naturally, if we apply the result that we obtained by continuity theorem, that is limit of mu a n equals to mu of limit a n, which is greater than equals to mu of A, just from the previous line, and mu of A is known to be infinity, because that is that we have considered at the very beginning. Now, since integration over E f n d mu is greater than equals to mu a n, so immediately we can write limit of integral over E of f n d mu equals to infinity, which is equals to integration over E phi d mu, which is less than equals to integration over E f d mu, since we know that phi is less than equals to f almost surely, or rather almost everywhere. So, from this line it is immediately clear that limit integration over E f n d mu is equals to integration over E f d mu, because this is actually equals to infinity. Now, we consider the proof second case, that means the most general case, which is that means we assume that integral over E phi d mu is less than infinity. Now, if this thing holds, then there exists a measurable set capital A, which is a subset of E with mu a less than infinity. In fact, this A is nothing but x belongs to E such that phi x greater than 0, such that phi equals to 0 on E minus A, because again this is almost everywhere. So, phi can be assumed to be 0 on E minus A. Now, let us consider two things. One is let capital M be the max over x belongs to E phi x, and for every epsilon greater than 0, for arbitrary epsilon greater than 0, set A n, just as in the previous case, we also define A n a sequence of sets as x belongs to E such that f k x greater than 1 minus epsilon into phi x for all k greater than equals to n. Again, clearly exactly the same way, clearly A n is increasing in n, union of A n equals to 1 to infinity contains A. So, naturally A minus A n is decreasing in n, and so since this is decreasing function of n, that means it decreases to union of A minus A n equals to 1 to infinity, which is nothing but phi, that is null set. This phi is a null set. Now, again using continuity theorem of probability, we have limit of mu of A minus A n equals to mu of limit A minus A n. Now, limit of A minus A n is null set, so mu of phi, which is equals to 0. Now, since obviously mu a is finite, that is less than infinite. So, when we get this limit of mu A minus A n is equals to 0, then we can always find an n such that mu of A minus A n less than epsilon for all k greater than equals to n, and obviously epsilon is taken to be arbitrarily small. Then for k greater than equals to n, we start with integration over E f k d mu, which is greater than equals to integration over a k f k d mu. Now, if we replace this thing, this condition from the or the construction from a k, we can immediately get which is greater than equals to 1 minus epsilon integration over a k phi d mu, which is again greater than equals to 1 minus epsilon integration over E phi d mu minus integration over a minus a k phi d mu. Basically, we replace this a by a bigger set E. That is why this greater than inequality is there, and this is almost everywhere. There actually is convergence is almost everywhere. So, taking this fact into account, we immediately get this entire quantity is greater than equals to 1 minus epsilon integration over E phi d mu minus integration over a minus a k phi d mu, just by simplification and replacing by this by a smaller quantity. So, let us call this as equation 1. Now, if we look at the extreme right hand term, that is integration over a minus a k of phi d mu, which is less than equals to m into integration over a minus a k, and naturally this means m into mu of a minus a k, and we have already seen for k greater than equals to m, this mu of a minus a k is less than epsilon. So, this entire quantity is less than equals to epsilon into m. Hence, from the first line, integration over E f k d mu is greater than equals to, and using this above this previous line and equation 1, we get integration over E f k d mu is greater than equals to integration over E phi d mu minus epsilon into integration over E phi d mu plus m. Now, epsilon is arbitrary. So, the above inequality is true for all k greater than equals to n. Therefore, if we take limit of integration E f n d mu, which is equals to limit infimum over k greater than equals to n integration over E f k d mu, and from this first line we can immediately write this is greater than equals to integration over E phi d mu minus epsilon into integration over E phi d mu plus m. Now, this right hand side actually is not depending on n, and since epsilon is arbitrary, so this entire quantity is less than infinity. This entire quantity is less than infinity, that means this is a finite quantity, that means integral over E phi d mu plus m is a finite quantity, and since epsilon is arbitrary, so we can make the extreme right side as arbitrarily small. Hence, we can get limit of integration f n d mu is greater than equals to integration phi d mu, and hence the theorem is proved completely. So, this is the Fatou's famous Fatou's lemma. We have proved both the cases when integral is equals to infinity and when it is less than infinity. Now, I will just state another theorem which is an immediate consequence of this Fatou's lemma, or we can say that we can state Fatou's lemma in an alternative way, that is in terms of random variables. So, this theorem is nothing but Fatou's lemma for random variables. So, let us consider x n be a sequence of random variables, y and z two other random variables on a probability space. Then, if y less than equals to x n and y is integrable, then we can immediately write expectation of lim lower bar, that is lim of x n less than equals to lim of expectation of x n. Direct application of Fatou's lemma, we will get this, because x n is a measurable function. Again, if x n less than equals to z and z is integrable, then we can write expectation of lim sub or lim upper bar x n greater than equals to lim sub of expectation of x n. And if we combine both a and b, that is, if we have y less than equals to x n less than equals to z and y z are integrable, then x n converges to x almost surely, then naturally we will get this. Just combining this a and b, we can immediately get limit n goes to infinity expectation of n equals to expectation of limit x n. So, here we see that although we have proved Fatou's lemma for a general measurable function defined on a measure space, we can immediately apply this Fatou's lemma and restate it in a different way, that is in terms of random variables, because random variables are also measurable functions with respect to a probability space. So, immediately we can see the importance of Fatou's lemma in proving some convergence relating to the random variables, especially the expectation of random variables. So far, we have discussed mainly Fatou's lemma, although we started with the definition of integrations with respect to a measure. So, Fatou's lemma is basically related to the sequence of integrals, or rather the convergence of the sequence of integrals, whether we can just put this limit inside the integral sign, or whether we can take it outside the integral sign in a very simple way. So, that was the idea of Fatou's lemma. Now, one of the most important consequence, or rather one can derive another interesting thing which we have just seen, that we can extend this Fatou's lemma, or we can interpret this Fatou's lemma in terms of random variables, because as we know that random variables are also measurable functions. So, we can always apply this Fatou's lemma to a sequence of random variables, and we have seen that the next theorem, rather the second theorem, is basically related to the random variables and the Fatou's lemma, which is which when applied to random variables, what is the form of this lemma. And we see there is a nice presentation of this Fatou's lemma in terms of random variables, and we can also define the convergence of the sequence of random variables using this Fatou's lemma.